Started talking about state space systems modeled either as, for example, in the continuous time, x dot equals ax plus bu. We reviewed matrix and linear algebra and understood that because these are matrices, so the solution of this equation is not as, it's related to like a scalar equation, but it's slightly different. So the solution for this state equation is xt equals to exponential function to the power of a matrix x0, this is the free response, and then the forced response relating to the input u of t. So we talked about the concept that here, in both the free response and the forced response, this term, this transition matrix EAT is very important. So we understood that first it is a matrix, right? We understood that the definition, how this is defined, is from the tile expansion. So it is actually a series. Etc. So it is a series, and then when they sum up, they converge. We talked about using this formula. We talked about two cases. First is if A is diagonal, then things are, this is the best thing we can expect. If A is diagonal, then this is diagonal, all these are diagonal, then EAT is diagonal. Now, the next best thing for us is Jordan form. If it's not diagonal but is in this form, let's say lambda, 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 1, 1, then it's still sort of nice because we can decompose into a diagonal matrix, and a matrix we say, we use capital letter N here, is nilpotent. So if you put this into the series expansion, then the nilpotent matrix, the powers, if you power it up, it's going to go to 0. So it's still very nice in that sense. We also talked about, quickly, like the concept, if it's not structured, so these are all very well structured matrices. If it is not structured, then what we do is we had this similarity transformation or diagonalization. So this is through similar transformation. Right? So this technique is very useful. It will give us a near diagonal or Jordan form from an unstructured matrix A. And then we can use this kind of result again. So this is the topic for today. And then the second topic for today is we're going to also take a look at the discrete time case. So it's xk plus 1 equal to axk plus b uk. We're going to take a look at how the solution here looks like. All right. So any questions before we start? Now, let's do a quick exercise. Something that I trust you guys are very familiar now. If you have a mass moving on a straight line without friction, let's say the position is x1 and the velocity is x2. So x1 dot equals x2. This is the velocity. So this is a model. Derivative of x1 equal to 0 times x1 plus 1 times x2. So this is the velocity equation. And then if there's no friction, then the mass is going to continue moving on the line. The derivative, the acceleration is 0. dx2 equals to 0. So it's a very ideal case, but for this exercise, we wanted to take a look at the technique that we have learned, how we can compute this one, e to the power of at. Do the Tyler series expansion. It's I plus at plus half of a squared t squared, right? And then keep adding up. So we talked about last time this 3 by 3 case. We said it's 1, 1 here is nilpotent. So 2 by 2 case is like this. So it's 0 in the diagonal and then 1 in the off diagonal. Very easily you can check that a squared is 0. So the only thing that remains is I plus 0, 1, 0, 0, t. You can check whether this makes sense, right? So this is essentially saying xt equals to this one times x of 0. x1 of t equals to 1 times x1, 0, right? Plug this one to here. x1 equals 1 times x1 plus x1 0 plus t times x2 0. And then x2t equals 0 times x1 of 0 plus 1 times x2 of 0. You can see whether this makes sense. So this is saying the velocity as a time function is the same as the initial condition if there's no friction, right? So the acceleration is 0. Velocity is constant. And the position is initial velocity plus t times the velocity, constant velocity. So from physics, this makes sense. Now this is the technique, a quick recap of the technique using Taylor expansion. Now, in practice, it's usually not the case that we have a diagonal or Jordan form of matrix. So I'm going to talk about two things. The first is more from physics. So this is, I wanted to give you guys a little bit of intuition about the A matrix, taking this one as an example, like how we can read this matrix A in terms of a system perspective. So the technique is called column solutions. So after this one, I will talk about the technique here. If it's completely unstructured and the matrix, let's say it's 3 by 3, 4 by 4, 5 by 5, so it's no longer, it's not as easy to see, to visualize the solution for a lower order case like this. All right, so two techniques. Let's take a look at this one. X dot equals AX. Let's say A is 0, 1, 0, negative 1, and X has an initial condition X naught. The solution looks like this, right? I don't have any input, so the solution is entirely the free response. So let's say x1 of 0, x2 of 0, this is the initial condition. Now, let's think about this matrix. This is 2 by 2 matrix. So it has two columns. First column, let's denote it as A1 of t. It is a function of time, right? In the previous example, you see this has to be a function of time. And then let's say the second column is A2 of t, another function of time, a vector function of time. If you treat EAT as combinations of columns, then EAT times x0 is actually A1t times the initial condition for x1 plus A2t, the second column, times the initial condition of x2. Just a different way of writing it. So the dimensions are, very carefully, A1 has two elements, two rows, and A2 also has two rows. It's a 2 by 1 vector. So from here, people actually developed a way to quickly derive the two columns, A1 and A2. The exercise is like this. So if you take a look at the result, if you let the initial condition to be 1, 0, so the second term is 0 and the first one is 1, then you can see the second term, A2t times x2, 0, is going to disappear. The total response, xt, is nothing but the first column of the EAT matrix. Right? So you can actually design, let's say you can choose your initial condition. You release the system at this initial condition and then measure the response. The response is going to give you immediately the first column of the transition matrix. So you can design experiments to obtain the first column. Similarly, you can design experiments, let the initial condition to be 0, 1, to make the first term disappear and then keep only the second term. So in this case, xt, the total response, is only the second column of the EAT matrix. So that's the concept. Now for this case, you can see here it's relatively easy, right? You can quickly write down how the solution would look like if you set the initial conditions to be 1, 0 or 0, 1. Let's take a look. So set the first case, 1, 0. Let's see how the system equation looks like. So the system equation is nothing but x1 dot. It's 0 times x1 plus 1 times x2. So x1 dot is x2 of t. And then x2 dot is the second row times this column. So it's 0 times x1 of t minus x2 of t. So this is the system equation. And then when the initial condition is 1, 0, so we can write out how the solution looks like, right? If x1, 0 is 1, x2, 0 is 0, what is the solution, let's see, for this equation? It only depends on x2, so it only depends on the second element here, second row of the initial condition here. If the initial condition is 0 and the derivative of x2 is negative x2, then it's always going to be 0, right? So it starts at 0 and then it doesn't have any acceleration. Its acceleration is 0. So xt is going to be 0 here. And then let's take a look at if x2 is 0, what will x1 be? So x1 starts as the initial condition of 1, and then its derivative is always 0. So it's not going anywhere. It's going to stay at 1. Right? So this is from like physics tuition. So we can also rigorously write down the solution given these equations. How can we do? We have this we have this ordinary differential equation. What is the solution for this one? Right? We learned about if a differential equation has this structure, x dot is ax plus bu, the solution has this structure. It works for both a scalar case and then a matrix case, right? So this is nothing but a special case with b equal to 0, and then a is negative 1, right? So you can also use the formula. I will write down a little bit the key concept here. So x2 of t, if you use the formula here, it's going to be e negative, a is negative 1, right? E negative 1 t times x2, 0. There's no input, so it's 0, right? And x2, 0 is 0, so it is always 0. So that's how, if you want to rigorously derive, you can use these formulas. So after you get x2, you can do the same for x1, right? x1 here is x1t equals what? What is a here? It's 0, right? So it's the coefficient for x1, right? So a is the coefficient for your choice of x over here. And here, for the first equation, is like 0 plus x1t. And then for this formula, you treat x2 as an input over here. Clear? All right? So then you can use the formula. It's going to be E0t x1 0 plus the integration 0t E0t minus tau bu tau. Bu tau is right here. X2 tau d tau. X2 is always 0, so it doesn't matter. And x1 is 1, so this is 1. This goes to 1, so the whole thing is 1. All right, two different ways you can derive the equation. So similarly, you can do the same. If x initial condition is 0, 1, how it's going to look like. So x2 dot, so it's right here, right? x2 dot in this case is negative x2t, so you can use the formula. You can use this formula. It's going to be E, so use this formula. E negative 1t times x2 at 0, then plus 0. So it's the same formula. But in this case, x2 0 is 1, so it's E negative t. Then plug this into here. So x1 dot, right? The first equation, x1 dot equals 0 times x1t plus x2t plus E negative t. So you can then derive either using this formula again, or just you can see that this is actually very simple. You're saying a function's derivative is E negative t, so you can get the function by integration as well. So this is the final result. So the key point for this example is that for these simple matrices, if A is not so complex, then you can actually obtain the first column. You can obtain the columns of EAT in this way. I do obtain the first column 1 of t from here by setting the initial condition, and then obtain the second column by setting the initial condition slightly differently. So now, if you get the basic idea here, you will have a deeper understanding of this example, this Jordan form example. So we derived the Jordan form by using the nilpotent property in this Taylor expansion. So we can do this. We can solve this EAT using the technique we just discussed as well. EAT, let's say it has 3 columns. These are all columns. So we can obtain the first column. I will do the first column over here. It can be obtained by letting initial condition to be 1, 0, 0. And then you see how the state's going to look like. So you have x dot equals ax becoming x1 dot equals to lambda times x1 plus x2. And then x2 dot is 0 times x1 plus lambda times x2 plus x3. And then x3 dot equals lambda times x3. I know how this is the choice of initial condition. And then we can solve from these 3 differential equations how xt looks like. And that's going to give us a1t. So let's see. By observation, some of these are very easy to solve. Which one is the easiest? I think this one is the easiest, right? So what's the solution for this one? x3 of t? Say that again, please. times x3 0, and then nothing else. There's no input for this if you treat x3 as the variable. So x3 0 is 0, so this is entirely 0. Now if x3 we obtained, then x2 is easy. This gives us x2 dot equals lambda times x2. So using the same logic, x2t is going to be what? Also 0. Now the only thing left is x1. Any questions for now? For x1, we have x1 dot equals lambda times x1 plus x2, which is 0. This gives us what? x1 of t is e lambda t x1 of 0, which is, so take a look at here, x1 of 0 is 1, so it's e lambda t. Yes?
Can you slide the paper up just so the turns get back? Yeah,
No
thanks.
problem. Yeah. We have solved x1, x2, x3. So that means a1 of t is, so a1 of t is therefore x1t under this initial condition is e lambda t, and then 0, 0. All right. This is a concept. Let us take a quick exercise. Why don't you guys derive A2, and then I will work on A3 on the screen. All right? This is your in-class exercise. All right, what you got? I got my A3 is half of t squared e lambda t, t e lambda t, and e lambda t. What you got for A2? Say that again. All right, excellent. So this is the result. If you go back to the previous lecture notes, this is also the result you're going to obtain using exactly this Taylor series expansion. Now, so up till now, I guess you guys have a basic idea of what are important for state space analysis. this equation is really important. If you have an input, if your ordinary differential equation has an input term, then the solution looks like this. Using that formula over here, right? So this equation is a first order ordinary differential equation with a equal to lambda and then input equal to 0. So it's e lambda t times the initial condition. For this one, this is a first order ordinary differential equation about x2 with x3 as an input, right? Because x3 is an input, so just plug in. So this is all the bu term on the left-hand side. We just put it into the integral. Similarly, for x1, treat this as the input, and then it's going to appear here. Now, what is interesting in this problem, in this example, is if you take a look at how the t term appears, you're going to see exactly the reason why we have t and t squared term. It's because of the integration, right? So it happens when we compute the integrations over here. For this one, this is what I derived, and using exactly the same formula. After I got x3 is e lambda t, this is the input term for x2, right? So x2, you got the e lambda tau term over here. It cancels out with e lambda t minus tau, the minus tau here. So you got e lambda t, right? So x2 is integration. So x2 0 is 0. x2 0 is 0. And then it's integration of e lambda t. It is because of this integration sign you have the t term coming up. And then when x2 is an input to x1, then this term, this is an input term. This input term goes to another integration. So this t gets integrated again, becoming t squared. That's how the t function appears in this Jordan diagonal term. All right, so that's the basic concept about if your matrix is simple enough and you can try with this setting, choosing the initial conditions and then getting the columns out directly. Let's switch gears and talk about the discrete time case. xk plus 1 equal to axk plus buk with some initial condition x naught. The solution for this one is actually easier. So there's no exponential function inside, but this is basically, if you write out a couple of terms, you're going to understand the iterations inside. So let's say x1 equals, so this is k equal to 0. x1 equals a x0 plus bu0 when k is 0. So keep doing it when k is, now we have x1, right? So I know the initial condition, I know the input, so I know x1. Then we can know x2. So just set k equal to 1, we know x2 equals ax1 plus bu1. And then just plug in what x1 looks like in here. So it's going to be ax0 plus bu0 plus bu1. All right? So it's a squared x0 plus ab u0 plus bu1. So just keep doing this and then you will find the pattern. So x3 is ax2 plus bu2, and then just plug in x2 inside. Then you're going to get what? Take a look at the pattern here. For x1 is a times x0. For x2 is a squared times x0. So for x3, you can see you have a times this one inside, you're going to get x a squared times x0 plus a times ab, so it's a squared b u0 plus ab u1 plus b u2. So you can keep on continue doing this. Then you have all the values of x for any k. So the structure, you already see how the free response looks like. So the free response, depending on the initial condition, actually has this interesting structure. It's a to the power of whatever k is, whatever x3, in this case, it's k plus 1 is sitting here. The general formula is, we can write if x k plus 1 for here, let's write xk just for better notation purpose. So from here, from all these, you get xk is going to be a to the power of k x0 plus the input response. All these are related to the input. And the structure looks as follows. It is a bunch of, so take a look at here. So it's b, ab, a squared b. And then if you continue doing this, you're going to get a to the power of 3b, etc. So it's b, ab in a matrix formula. Times u, so b is always multiplying the closest input. So it's u of k minus 1, right? So u2 here, if k is 3, then u is k minus 1, times uk minus 2, so just keep reducing the index all the way to u0. This is nothing but u, like linear combinations of these columns, right? So it's linear combination of b, ab, a squared b, etc.
Professor, would the last term in the vector be a to the k times b?
This one? Okay, that's my question actually. What is the last term over here? A to the k minus 1b here. Let's take a look. For this k equal to 3, we get a squared. So it's k minus 1, so it matches, right? If we go to here, if k is 1, then it's a times a to the power of 0 times b. So it's a k minus 1. So that is the solution. Question?
For the general x of k equation, should the first element of the u vector just be u of k?
This one over here? Okay, that's a good question. What do you guys think? What is the index for here? So some of your classmates said it should be k. Do you agree or disagree? Some are nodding. Some thinks it's k. Who thinks it's k minus 1? You think it's k plus 1. K minus 1. What's your reason?
Because we started off, instead of using the a cubed or the highest a thing, when k is equal to 3, we used k directly. So k is equal to 2, it gave us a cubed. But in our case, we used k directly to be k, so it becomes a to the power of k, so that thing will be uk minus 1.
Right. I think, exactly, I agree with you. I think your classmate, your observation is, I use notation k equal to 2 here. You think this is 2 here. So the way that I wrote it is like that. But more deeply, I think the intuition, I wanted to give you guys a little bit understanding of the intuition. So when we see this definition of state equation, what are we saying? We're saying that the input at time k does not impact my state immediately. It impacts my future state one step later, right? Which is usually nowadays the case, right? Computers, if you send a command to a computer, it's going to wait for one sampling time to make things work. That's why when you check, if you want to check, then this should be k minus 1. So that is the derivation. So the general case, so you can simply derive similarly, like if the initial condition I count from k sub naught, then it's going to be k minus k naught, and then the index is here, so I wrote it. So it's again b, a, b, and then all the way to a some power times b, and then multiplying inside. So I write it reversely in this case. So I wrote b at the end and then put a to the power of something times b at the front. So this similarly needs to swap the orders. The last term is gonna, my last term here, uk minus 1, is my first term in this vector is his last term in this vector here. And then my last term, u0, this is the initial input. It is similarly here, right? So this is looking at the initial time k0. All right. So you can write it in this form. You can also write it in a summation form, similarly. So the summation form, this is summing from j index from k0 to k minus 1. The first term, when j is k0, you got a k minus 1 minus k0 times b, and then uk0. Just a different way of writing it. So this is another equation that's pretty handy. So for this one, I don't have enough space. Now you guys have the solution for both continuous time and discrete time systems. Similarly, this is a free response, this is the forced response, very similar to the structure here. Now, because of the solution structure, you can see similarly this transition matrix for discrete time case is also very important. So we want to find out how a matrix to the power of certain numbers will look like. So we're going to do exactly the same way. We're going to work on a structured matrix, diagonal or Jordan form, and then unstructured matrices. So the structured matrix is straightforward. So if A is diagonal, then A to the power of any number, k, is also diagonal. This is in the continuous time case, we talked about this. So it's just to put in powers into these diagonal elements. Now if k is Jordan form, if A is in Jordan form, we can do similarly, we can expand this A to the power of k term by decomposing A into a into a diagonal matrix plus a nilpotent matrix. So the idea is when you multiply things out, you're going to need to consider n to the power of some numbers. And then because n is nilpotent, then a lot of terms is going to vanish. So let's take a look at the details. You know how A plus B, let's say square, looks like, right? It's A square plus 2AB plus B square. This one, a matrix form to the power of k, if you write it out, is actually this. it is the first element to the power of k, and then in the end you're going to consider the last element n to the power of k. Now in between is computed this way. It is like, if you write it out, so you have k multiplications here. You have k terms multiplying together. So what is the term that will appear with n to the power of 1? It is this element times this one, times this one, times all the first terms about remaining terms over here. So you choose the second element here and then choose the first element in the remaining terms over here. That's one way to generate n. What is the other way to generate n to the power of 1? It's you choose the first term in here and then choose n in here, and then the remaining you choose the first term, right? So there are k ways to choose. You have k multiplying terms. So it's k times n and then lambda I3 to the power of k minus 1. So this is a combination problem. Choose 1 from k. For n squared is similarly, you choose from k terms, from k multiplication terms. You choose from this k2, that's going to give you n over here. So you do get n squared, and then all the remainings you choose lambda times I3. So that's n2 and then lambda I3 k minus 2. And then there are two combinations way to get it. So this is equal to half of k minus 1. That's how two combination works. All right, that's the basic idea. So once you understand how the terms appear, how the power terms appear, you can quickly recognize that because n is nilpotent, n to the power of 3, all the higher order terms is going to disappear. Right? So you actually don't need to write this out at all. These are all zeros. So that's the concept. So what's left is lambda I3k, which is lambda k, lambda k, lambda k, and then k times lambda k minus 1, lambda to the power of k minus 1, times n. N is right here. And then you only need to compute this extra two combination term. So it's n squared becoming 0, 0, 1. So this is like matching to the right. So you get 1 going to the top right, and then all the remainings are 0. All right, that's the structure. Take a look at the final solution, and we'll take a quick break. Let's take a look at this one. If A is unstructured, what do we do? We're going to talk about the continuous time case, and then we're going to talk about the discrete time case. The most important thing, the starting point of doing this generalized matrix is the similarity transform that we talked about in linear algebra review. It is to look at the problem slightly differently. So look at the problem in a so-called new state space where my state of choice is x star. So we talked about the concept of matrix transforms one state space to another. So we don't know T yet. It's going to come up once we have a basic idea of what kind of property we want in x star. So we're going to have some nice property of x star, and then T is going to appear naturally once we understand what we want. So what do we want from this transformation? Right? So let's see, it's going to be T x star dot equal to A t x star plus b u, or when t is invertible, it's going to be t inverse a t x star plus t inverse b u. Let's talk about what we want. Let's say this matrix is lambda, and then this is b star. So what we want is, we know how to solve a matrix. So this equation has a solution. X star t is E lambda t x star 0 plus the input term, right? So I won't write it again, but this is the input response. My point is, for this part, right, it contains E lambda t, and we know how to compute E lambda t if this matrix is diagonal or is Jordan form. So that's what we want. We want this to be able to have a structured representation, either diagonal or Jordan. Right? For now. So then it works out. This is exactly like the similarity transform. A matrix, a general matrix A, can actually be simplified, have this diagonal or Jordan form representation using the eigenvalue, eigenvector tools. That's the big picture for this part. So let's fill in all the details. All right. So detail number 1. First is be careful about the initial conditions. So these are all we have talked about on the board over here. First, detail number 1 is be careful about the initial condition relationship. If I know the initial condition for x, then the initial condition for x star, which we need to use, right, is t inverse times x naught. And the second, a few more details is essentially here. So we talked about, let's say, for simplicity, the input is 0. So we just have the free response that we need to consider. So we talked about, we want this to be diagonal or Jordan. So let's say 2 by 2 case. Let's say lambda is lambda 1, lambda 2, this lambda matrix. Then you know that x dot t is E lambda t times x dot x star 0. So is E lambda 1t, E lambda 2t, because lambda is diagonal, capital lambda is diagonal, times the initial condition. Is multiply things out, is E lambda 1t times x1 star, E lambda 2t times x2 star. Here, from the definition of the state relationships, x is t times x star, and we have computed x star, right? Then we would know that xt will be equal to t times x star t, which is E lambda t times x star 0. And then because the initial condition we talked about the relationship is t E lambda t, initial condition x star is actually t inverse x 0, right? This is the result from the last slide. Then we know that this one, or here, it's actually easier, right? Because the response for xt, the response for this one, we already talked about, it should be EAT times x0. And then we derived this result over here. It can be expressed also as TE lambda t times T inverse. So it must be that E lambda t, EAT must be equal to this T times E lambda t, T inverse. So that's the result that we're going to use. We have derived a way to write down EAT using a diagonal or close to diagonal Jordan matrix times T, matrix T and its inverse. All right, this is easy. E lambda T is simple. It's structurally simple. So that makes the whole computation to be straightforward. Any questions? All right. So this is similarity transform. A matrix A, if you can write a matrix A and lambda by this relationship with T inverse T on the left, on the right, then A is similar to lambda. So similarly, in this case, this is saying that E lambda T is similar to EAT. There are two similar matrices defined by a similarity transform. Now let's figure out the details, how to compute T and how to compute lambda. So this is the eigenvalue approach. T is defined by the eigenvectors, and then lambda matrix comes from the eigenvalues. So we talked about how to compute eigenvalue lambda is the solution to this determinant equation A minus lambda I, determinant equals 0, and then the eigenvector is the solution to this AT equal to lambda T equation. Or if you prefer, you can write it as A minus lambda I times T equal to 0. All right, so let's do an example. And we will see quickly how these all make sense. So this is a mechanical system with strong damping. This is saying x1 dot equal to x2, and then x2 dot. So this is like position derivative equals velocity. And velocity derivative, which is the acceleration, equals lambda 2, negative 2 times x1. So there's a spring with coefficient k. Spring times the displacement minus 3 times the damping, x2. So let's do computation of EAT for here using the similarity transform approach. So the question is, what is EAT for this case? Now let's do the eigenvalues first. Let's do it actually here. Determinant of A minus lambda I is the determinant of A is 0, 1, negative 2, negative 3, minus lambda I, so it's minus lambda, minus lambda. So the determinant of this 2 by 2 matrix is negative lambda, negative 3 minus lambda minus cross diagonal minus 2. So it equals 3 lambda plus lambda square plus 2. So I can see that this actually is lambda plus 1, lambda plus 2. So lambda 1, one of the eigenvalues is negative 1 and the other is negative 2. That's the two eigenvalues. I actually use the number 2 equals to 1, negative 1. So lambda 1 is negative 2. And then for the first eigenvector, let's say T1, so it's A minus lambda 1 T lambda 1 I times T1 equal to 0. So T1 is in the null space of A minus lambda 1 I. So we have A minus lambda 1 I is here, lambda replaced by lambda 1, so it's 2, negative 1, 1, negative 2 times T1. So therefore, T1 is the infinite solutions, so we pick one, right? So let's pick any one. Let's say one. Let's say negative 1/2 and then 1, which should work, right? So I choose this one. So anything actually will work. So you can put a k in the front, right? So if k, let's say, is negative 2, you get that solution over there. So for T2, it similarly is A minus lambda 2I T2. Then it's this replaced by lambda 2. It's going to be 1, 1, negative 2, negative 3 minus negative 1. So I can choose T2 as negative 1, 1. Okay? So negative 1, 1. Then with another scaling factor, k tilde. Any k tilde that's non-zero will work. So then with these matrices, so we're going to get T matrix, which is T1, the two columns T1 and T2 combined. And then the lambda matrix is lambda 1, lambda 2. Once you get T and lambda, then you can compute T inverse. So this is a 2 by 2 matrix. So the inverse, we have a formula. So it equals, so follow from here, it equals 1 over the determinant of this matrix, which is 1 times negative 1 minus 1 times negative 2. And then inside, using the determinant matrix law, using the matrix inverse law, is like that. Computing the determinant is negative 1 plus 2, so it's 1. So this is the inverse. Then using T, E lambda T, and T inverse, we can get the final solution. All right. So this is the case if we have two different eigenvalues, right? Lambda 1 is negative 2, lambda 2 is negative 1. So it doesn't always happen this way. Sometimes you have repeated eigenvalues, or if you have complex eigenvalues. So let's talk about the case if you have complex eigenvalues, what will happen. So for example, this case, if A is 1, negative 1, and then 2 by 2 matrix like this, what will be the solution? When we talked about the structured matrices here, we never talked about case like that, right? This matrix is not diagonal and is not nilpotent. If you go from this route, it's going to be a little bit more cumbersome. But the approach using similar transformation is going to be straightforward. So let's see. For this one, if you compute the eigenvalues, A lambda minus t, so it's going to be negative lambda 1, negative 1, negative lambda, right? So the determinant is going to be cross diagonal, or diagonal term multiplied becoming lambda square minus 1, so it's lambda square plus 1. So the eigenvalues are all complex, plus or minus j, the square root of negative 1. Right? This matrix is actually, it's not symmetric, it's called skew symmetric. So you have two eigenvectors, they are still different. So you can write down the eigenvectors by letting lambda 1 equal to j and lambda 2 equal to negative j. So you're going to get A minus lambda 1 I is going to equal to 0 minus lambda 1 minus j, 0 minus j, 1, negative 1. Or simplifying to be negative j, 1, negative 1, and negative j. So the corresponding eigenvector, the t, that sits in the null space of this matrix is, let's pick, I can pick quickly T1 to be 1 and then j, right? So then it's going to make 1 times negative j plus j is going to be 0. Right? The second term is the same. It's negative 1 times 1 is negative 1 minus j square. Negative 1 minus j square. J square is the negative 1, so it's also 0. So this is one of the eigenvector. Do the same for the second eigenvector, then you can obtain T2. It is actually the complex conjugate of T1. So you get T, capital T matrix, and then T inverse matrix from the matrix inversion formula is going to be negative j minus j, and then inside is negative j 1, negative 1, negative j, which is 1 over negative 2tj, 2j, negative j, negative 1, negative j, 1. So it equals this. J cross out, and then negative 2 multiply inside. The negative signs gets cancelled. These are the bottom line is you can obtain T and T inverse. Right? All the similar transformation techniques work. And then you just plug in into this formula. E lambda t, e to the power of lambda t is very easy again. So it's e to the lambda 1 is j, lambda 2 is negative j, so it's still diagonal. And then it's multiplying t and t inverse. Do this work, and then you can obtain, as an exercise, this solution. All right? We talked about the concept. You see e jt and e negative jt here. So we talked about concept of sine and cosine. They are just nothing but exponential functions using the Euler formula. So this is the result that you can verify. All right? So the conclusion is that if A is 0, 1, negative 1, 0, then the solution EAT is cosine t, sine t, negative sine t. This is the solution to this A matrix, to the system with an A matrix that has imaginary complex eigenvalues. Okay, let's see, what's the time? Any questions? The general case. So in the previous example, the eigenvalues are plus or minus j. The general case, if you have complex eigenvalue, is going to be somewhere, let's say here and here. So if you have complex eigenvalues, they always appear in complex conjugate. Is let's say sigma plus j omega, and then sigma minus j omega. So this is omega, this is real axis, this is imaginary axis. So in general, you have complex eigenvalues that look like this. Then you can show that the solution to E sigma, so this is not as symmetric as we want and not as simple as skew symmetric that we saw. This one is sigma sigma omega negative omega. Then if A looks like that, you can show that by the technique that we learned, you can show EAT is E sigma t cosine omega t, E sigma t sine omega t, negative E sigma t sine omega t, and E sigma t cosine omega t. This is by, again, some similarity transform T using this set of choice of eigenvectors. All right, so it works like in the previous case. If sigma is 0 in the previous case, you can see this actually goes to 1. So it actually matches the result that we just derived. If you guys notice, one of the things that I did not go through entirely is calculating the inverse for higher order systems. I give you all second order systems. So calculating inverse for higher order systems, you have done that. You have done 3 by 3, which is a lot of writing, right? What works tedious for humans actually is very beneficial for computers. The whole point of doing these kind of similarity transformations, the whole point of learning about the so-called modern control engineering is because these techniques, computers are just, this is like recipes if you think about it. All these, there's nothing tricky. You just compute eigenvalues, eigenvectors, then nothing weird is going to come up, which is what computer would like. So that's the key point in all these technologies. But in the same time, there he is, Ken, hi. So in the meantime, if you think about some of the technique we learned about if I know the way of deriving just the columns of the EAT matrix. That's a special technique. That's something that only we can do. Computers, they wouldn't do it that way. And that can be a lot of waste of computation or resources from time to time.